So, we know what a minimum spanning tree is, and Kruskal is a way of finding the minimum spanning tree. And practically, what we're essentially doing is laying cable between towns in the cheapest way possible. So all the towns have to be connected up. But it doesn't matter how you get from what. So like the internet. Actually, I don't actually know how the internet works, but like I don't know, something that goes through pipes, right? And so each house needs to be connected to every other house, but you want to do it as cheaply as possible.
Right.
Yeah. So you've got a subset of all of your roads, and then all pipes, and which ones are you choosing to use to make it as cheap as possible.
Useful.
Yes, very useful. I use it all the time. So, first of all, obviously we need to know what we're actually going for. So do you remember what a tree is?
A tree is a connected graph with no cycle.
Excellent. And obviously, if this was worth 1 mark, I would say a connected graph with no cycles.
Okay.
If it was worth more, I'd say, but what's a connected graph then?
I think it's where you have every pair of corner vertices connected by a path.
Yep.
Yes.
Well, you don't really need to say connected by a path. If you just say connected, so a connected graph is a graph in which every pair of vertices is connected.
So I'm allowed to use the definition in the definition?
Because you almost there used the word connected in a colloquial way. You said connected by a path, whereas connected is a technical word.
Right.
So what does it mean for two vertices to be connected?
A path is between them.
There is a path between them, yeah.
Yeah.
So in a way, you can't really say connected by a path, because connected means there is a path.
Right, I see.
Yeah? So there's a path between every pair of vertices. That's a connected graph. And what about cycles? What's a cycle?
A cycle is when the path is closed.
Yes,
like
closed
path.
Yep, closed path.
Okay.
And what do we mean by closed?
That the last vertex is connected to the first vertex.
Yeah, the end vertex of the final edge.
Okay. The final edge. Yeah.
Is equal to the start vertex.
Right.
Of the first edge.
Okay.
Yeah. What about path?
A path. Help me.
It's got quite a lot to it, path. It's a finite sequence of edges.
Yeah. Finite sequence of edges.
And you can't jump. So the end vertex of one edge is the start vertex of the next edge.
So that's that one, isn't it? That's that bit.
Well, this one, the closed path is specifically saying that the end vertex of the final edge in the sequence of edges in the path is equal to the start vertex of the first edge of the sequence of edges in the path. A path is a finite sequence of edges, and what we need is the end vertex of any edge in the path to equal the beginning vertex of the next edge in the path.
Okay. Edge.
Yeah. And what's the other extra piece of information about path? That's really important. So why isn't this a path, for example? If I go E, D, C, B, D, A, why isn't that a path?
Oh, you can't repeat. Because you haven't gone from A to E.
Well, I wasn't trying to do a closed path, I just was trying to do a path. So one of the really important facts of the definition of a path is no vertex can appear more than once.
No vertex can appear more than once. No vertex.
So I haven't repeated any edges.
Right.
But I repeated the vertex D.
I see.
Yep, so that's not a path.
Done.
Done. Okay, so that's a tree, all quite complicated. All very embedded. Spanning tree?
So a spanning tree is where it doesn't matter how many vertices. Well, you have to label the vertices, but it doesn't have to be, they don't all have to be connected. So just this part here is a sub-tree.
That's a tree, yeah.
Yeah, a tree.
Which that is a tree, which is a subgraph of the original graph.
Yes.
Yeah.
And if I did this,
that's another
tree, but if I did this, the whole thing is not connected, so therefore it's not a tree.
Exactly, that's not a tree, yeah. So what is a spanning tree?
A spanning tree is where you have all the vertices and some of them are connected by a path.
All of them are
connected
because
by a path.
it is a tree.
Ah, yes,
okay?
spanning tree, yes.
A spanning tree is a tree.
I'm doing a tree.
Yeah,
a spanning tree is all of them are connected by a path. Right.
Yeah.
So
well, a spanning tree is a tree.
Yes.
The important thing, the spanning bit, means it spans all the vertices. All the towns are included.
Yes.
Yeah. So the spanning bit, the only additional part that spanning adds to it, is that all of the original vertices from the original graph are in our tree.
Yes.
Yeah? Okay. Minimum spanning tree.
So a minimum spanning tree is the same, where all the vertices have to be included and a path has to be connecting them.
With no cycles.
With no cycles, but it has the minimum weight, so it must have the minimum length of the path between them.
Exactly. So we choose the cheap paths between them. Great. Okay, so Kruskals, here's Rusty, the clown, to help us do Kruskals. What Kruskal says is like, we're just trying to do this as cheaply as possible.
Yeah.
So what we're going to do is we're going to take all of the edges, which I have done like this, so that we can take them off, and we're going to line them up in order of size. So can you just get those ones from up there that I haven't got? And can you make a list, starting with the cheapest, or the one with the least weight, is what we say at the top.
So I think 8, and also we have another 8.
Doesn't matter which way around.
We have a 10, and we have another 10. 11, 12.
Yeah. Now what we're going to do is we're going to add these in until we've got a tree, a spanning tree, and it will be a minimum spanning tree because we've chosen the minimum we possibly can. Okay. So what we do is we line them all up like this, and obviously you just write them normally, and then we start adding them. So we write next to this, add. Okay. So what that means is we're adding BC in. BC is now added.
Yeah.
Okay. Now we're just going to keep adding them, and each time we add, we just make sure we're not creating a cycle, because if we create a cycle, we haven't got a tree.
Okay.
We stop when we've got a spanning tree. We're going to have a tree at all stages, or 2 separate trees or 3 separate trees, but they might not come together and be connected into a connected tree until a certain point.
Okay.
So we might end up with like dun dun dun, and then another bit here, and then this bit, and then slowly it will come together into a spanning tree. That's what's going to happen.
Okay.
Okay. So we add BC. Can we add AD, or would that make a cycle?
Can add
Okay.
AD.
So do you want to add AD? And I'll write add here. Okay. There we go.
Yeah.
Right. Shall we add DC?
We can.
Yep. That doesn't make a cycle.
No. So,
Oops. We both wrote it somehow. Right. What about AC? Can we add AC?
no, because that would make a closed network.
Path, a closed path, which is a
yeah.
cycle. So ACD would be a closed path or cycle. So we reject.
Okay.
Can we add EF?
Yes, we can.
Add. Have we finished yet?
No.
All the nodes are in, aren't they?
Oh yeah, they are. But
Yeah. A is in, D is in, C is in, B is in, E is in, F is in.
But E and F aren't connected
Yes.
to anything.
So it's not yet connected. So we need to keep going. So can we add CE?
Yes.
Yes. Okay, so we can add that one in. Add. Now we can stop.
Yes.
So we've now got a spanning tree, all the nodes are included, and it's connected, so we can stop.
Yep.
And then we have got there a minimum spanning tree.
Okay.
That was the smallest it can be. Okay, ready to try one yourself? Oh, these are just examples. You know, I said at the beginning, like your BC and your AD, they're both 8.
Yeah.
So, and these are both 10. Does it matter which way round? No. But you will end up with different trees, but they are all minimum spanning trees, because all of these have got the same total weight, which is the smallest total weight that you can get for this particular graph. So it doesn't matter whether we add, the 10 that goes from C to D or the 10 that goes from A to C. all of these are different spanning trees, but they are all minimum spanning trees. So minimum spanning trees aren't unique.
Right, I see.
Okay. So
Right.
this is it.
So I need to build up a list.
Yep. Good.
Right. So A to B is 36. Is this how I need to write it?
Well, what's the objective with our list?
We're trying to collate all the paths connecting each.
Yeah.
node.
And then we're going to pick.
So I don't really need the number, do I?
Well, the number. No. Well, actually, let's look back. Do we need the number?
We didn't
Not
use
really.
the
We
number.
didn't use the number, did we?
Sure.
But like, how did we get them in that order
We
in the
sorted
first place?
them.
Yeah, we
Sorted them. Right, so I need
Yeah.
to sort them again. Right, there's a lot to sort.
Yeah,
Okay.
yeah. So you need some sort of strategy for getting them all in. And this is the, in essence, this is the hard bit.
Okay.
Yeah, if you can get these in a list where you haven't missed any and they are in ascending order, well done.
Okay, so if I start with A, I can do it in order what A connects to. So A to B is 36.
Yep.
Do I disregard 58 because 36 is smaller, so presumably I need to use
Well,
that.
let's have another look back what we actually had here. What was this? A list of?
Oh, that was all pathways.
Yes,
so I need
all
to
of
do
them.
all pathways.
Absolutely all of them in ascending order.
Yeah.
Because
Okay.
then we can start with the smallest one and start building them in.
Okay, cool. So AB 36, AB also 58, AC 23.
Is this going to go in order later?
Yeah.
All right.
Is that alright?
Yeah, it is.
Is
Yes.
this where I would use
Yeah.
bubble sort?
Well, you could use a sorting algorithm to get them in order. To be honest, I think probably what I usually do is I just look for the smallest one and write it down,
Ah, you do it that way.
and then put a circle around it or something like that. Just
Yeah.
yeah.
Okay, cool.
Because
Let's do that.
otherwise it can be quite a
Laborious.
long job. Yeah, exactly. So can you see?
So 23 looks like the smallest.
Okay, so you write down AC
So
23.
AC 23,
Okay.
and then we look. Oh no, 22.
Yeah, but it doesn't matter. So you can write it above.
Right. Okay.
Yeah.
22, and then we've got 28. I think 28, and that's BC.
Yeah.
So that's that, and then 31 is CF. Right, yeah, this is much better than my way. My way is rubbish. Right, 31, 35 is D to E, and then we've got 34 is
Squish it
so
in, squish it in.
FG,
Yeah.
34,
Yeah.
and then we've got 38, 36, which is 36.
Yeah.
And we've got 43, no, 38 again, E to G. Sorry, not again, just 38. And 39, C to E.
Let's create a bit more room.
Okay. And yeah, right, this does take a while, doesn't it?
Yeah.
43, 47, yeah, 43, so D to G. And G to H. And then 51, 46, B to F. So is this what I would have to do on my
Yeah.
exam?
Yeah.
Okay. And how long does a normal student take to do this on their exam?
I'm not sure.
Right. Right, and then we've got D to G. 1 again. Where's D to G? And then finally, A to E, 58. Done.
Excellent.
Right. Cool. So now, I need to start drawing pathways. So,
Yeah, but
A
if you
to
were
E.
my student,
Yeah.
then what you would be doing now is that you would be making really sure that you haven't missed one, because if you didn't check and then you handed it in or whatever and you'd missed one, then it would be like really bad.
Yeah, you're right. I'm sure I did it right, but right, okay, so how many have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 pathways. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.
Yeah. Now you're circling things really good because you can see which one you haven't circled.
Ah, 47. Fantastic. D to C, 47. Oh, I would have there, right?
Yeah.
Stay there.
Yeah.
Okay.
Right, we're ready to add. So
Right.
you start add, you only reject if it's going to make a cycle. So it's a good idea to have, sometimes in the exam they give you these anyway, but to have a little thing drawn out and add them as you add them, because then it's really obvious if you're putting a cycle on accidentally. So all of them?
Yeah.
Okay.
AD. Go up to G. Oh.
Okay, so
First one's AD.
add. Yeah, done.
Done. And then AC, can do 23.
Yeah.
Add BC.
You can just look at your diagram that you're doing, then it's really
It is, isn't it?
really clear whether or not you're making a
BC,
cycle.
add, and then CF. Yes, okay.
Yeah, it's not a cycle.
Add, and then FG. I can.
That's G.
Oh, sorry. Thank you. That was E.
Yeah.
F to G, okay,
Yeah.
do that. And E to E, can do that.
Yep, doesn't create a cycle.
And A to B, no, I can't do that.
Reject,
Yeah.
because that creates a cycle.
Can I just put R and A next to it?
Well, I don't know is the answer to that.
Okay.
When students start doing R and A, I take a mark off and say right, add and reject.
Right, okay.
But I don't honestly know whether or not the examiner would.
Okay. I think I would reject E to G because that would close the cycle, right?
Yes, the cycle you'd get for that one is if you closed EG, you'd get this cycle.
Yes.
Yeah, that's a cycle. So you can't have that one closed
Okay.
up there.
Right, so the only thing I'm missing is the H, isn't it?
So C
So can I
to E,
skip-
are you rejecting C to E?
Yeah,
as well?
because I've included,
Yeah,
but
yeah.
I know I've just got to
Yeah.
get to the ones with H, so I'm just going to go G to H, add, and
Yeah.
then all the others close the
Yeah,
line up.
and also it's not only that you've got all the nodes, it's that it is a connected graph
Yes.
as well. It's not, you haven't got two separate trees growing. You've connected everything together.
Yes.
Perfect. Okay,
Cool.
right. In your pack, you've got these. Oh no, sorry. Yes, before you do the two that you've got. So there's two ways. On the next video, we're going to look at prim, finding the minimum spanning tree. And one of the things is why would we use Kruskal or why would we use prim? And so some of the differences between them. So Kruskal can't be applied to a matrix, which prim can, which you'll see. Kruskal has to start with the smallest arc. You have no flexibility about where you start at all, whereas with prim, you can start anywhere, which is an advantage.
Okay.
If you want to start at a certain town and you definitely, or a certain arc, if you definitely want to include something, you can start with that particular arc, node and then go from there. Kruskal, as you saw, it brings in one arc at a time,
Yeah.
but you keep needing to check the cycles. Whereas when you do prim, it brings in a node at a time. It's just a different way of thinking about it. It's the same thing. If I've got A here and I do this, then when you're doing Kruskal, you're thinking, I have brought in AB.
Yeah.
Whereas when you do prim, you think, I've brought in B.
Yeah.
I had A, now I've brought in B.
Yeah.
So you're thinking in terms of nodes, and you never have to think about cycles. There's
Yeah.
no need for it. Whereas with Kruskal, you're thinking in edges, and you're bringing in edges, and you do need to keep thinking about cycles. So they're the main differences between the two. Okay, so in your pack you've got these two. So you're going to pause the video now and have a go at these two Kruskals, and then I'm going to put the answers up in 5 seconds. So pause the video, have a go yourself, and then look at the answers. Okay, so here's the answers to the first one, and yours should be identical to this, unless I've done it wrong, because there should be no variation. There's no opportunity for having your own opinion or anything, and the total weight of the tree is given. And the next one, these are the answers to the next one. Again, should be absolutely identical with the same total weight if you add it up correctly. Okay, next video is about prim, same minimum spanning tree, but different method.